Hi everyone. In the last lecture, we have discussed a few consequences of the spectral theorem for compact self-adjoint operators. Today, let us look at some more important consequences of the same result. So, let us quickly recall the spectral theorem for compact self-adjoint operators. If K is a compact self-adjoint operator, then there exists an orthonormal system of eigenvectors of T. Let us call them as phi 1, phi 2, phi 3, so on. With corresponding eigenvalues lambda 1, lambda 2, lambda 3, so on. In fact, we can arrange them in the increasing order in modulus such that Tx can be represented as summation n equal to 1 to infinity lambda n inner product x phi n with phi n for every x in H. So, and we have shown that if lambda n is an infinite sequence, then lambda n converges to 0, and the series on the right side of the equation star converges in the operator now. Okay, now let us look at some more important properties. So we have seen that H can be represented as null space of T, orthogonal direct sum with null space of T minus lambda Ki per K equal to 1 to infinity. Now the same result we can write in a different way. Let K equal to K star be the compact self-adjoint operator. Let mu K be a non-zero eigenvalue of K, and let us write Pk as the orthogonal projection onto null space of K minus mu Ki. Then we have the following. Then we can conclude that Pk Pj is 0 equal to Pj Pk for every j not equal to K. We have P naught x plus summation K equal to 1 to infinity Pkx equal to x for every x in H. So where P naught is nothing but an orthogonal projection onto null space of K. K can be represented as summation mu K Pk so here the convergence, the series it converges in the operator now. Okay, so we are putting the same spectral theorem in a different way using the orthogonal projections onto eigenspaces. So we have Kx equal to summation lambda n x phi n by the spectral theorem. We know that null space of K minus mu K, this is finite dimensional, and this is spanned by phi n1, phi n2, so on phi np, where this is subset phi ni is subset of that phi n's that we got, and in fact lambda n equal to mu K for some K. Now null space of k minus mu ki is finite dimensional. So let us take pk as the projection onto null space of k minus mu ki. Now we know that if eigenvalues are distinct, the corresponding eigenspaces are orthogonal to each other. So from that we can conclude that pk pj is pj pk, that is 0 for all j not equal to I. Okay. Now let us look at the other part, that is if you look at, so we have already seen that H can be written as null space of K plus orthogonal direct sum of null space of K minus mu Ki, K equal to 1 to infinity. So from this we can conclude that X can be written as P naught X plus summation K equal to 1 to infinity pkx. And here the convergence is with respect to the strong operator topology, namely it converges pointwise for every x. And if you look at k of so we have k into pk, pk into k, because every eigenspace is reducing for k, so we can conclude that k pk equal to pk into k. And on pk, when x is in range of pk, then we can conclude that kx equal to mu ki. So this is exactly mu k. You will get mu k pk. Okay. Now from this we can actually look at norm of k minus summation k equal to 1 to n mu k pk. So that is nothing but supreme of norm of kx minus summation k equal to 1 to n mu k pkx x is in the unit sphere of h. Now this we know that this is supremum norm x equal to 1. So this is nothing but summation k equal to n plus 1 to infinity mu k pkx. And this we have already seen that this is less than or equal to supreme of mod mu k into norm x. This we can easily show. And we know that this mod mu k converges to 0 as n tends to infinity. Hence we can say that k can be represented as summation k equal to 1 to infinity mu k pk. So we can represent a compact self-adjoint operator using orthogonal projection onto the corresponding eigenspaces. This is one more version of the spectral theorem for compact self-adjoint operators. Okay. Now we can ask the question, what will happen if we replace self-adjoint operator by a normal operator? So compact normal operators. To prove the spectral theorem for self-adjoint compact operators, we used three things for self-adjoint compact case. We used three things. The first one is numerical radius of t is exactly norm of t when t is t star. And the second result that we use that either norm t or minus norm t is an eigenvalue for t when t is t self-adjoint and compact. And the third result we used is that null space of t minus lambda I reduces t if lambda is in the point spectrum. Using these three results, we were able to prove the spectral theorem for compact self-adjoint operators. Now, in fact, all these results are also true for normal operators. Hence, we can actually get a spectral representation theorem for compact normal operators also. So, let me quickly recall these results. Let theorem. Then we have already shown that the numerical radius of t is exactly norm t. So this is already proved. And second theorem, now using this result we can actually show that if t is compact normal, then we can show that there exists lambda in C such that there exists a complex number lambda in the point spectrum of T such that mod lambda equal to norm T. In the earlier case we got since lambda is a real number, so we got either lambda equal to plus norm T or minus norm T. Here lambda is a complex number, so we get mod lambda equal to norm T. And in fact, using the same proof we can actually prove this result. And the third result, so this is follows as in the case of self-adjoint compact operators. The next result we can easily show that is that if T is compact and normal, we don't need compactness here. If T is normal, then and lambda is in the point spectrum of T, then we can show that null space of T minus lambda I reduces T. This we can prove. So lambda in the point spectrum of T implies null space of T minus lambda I is non-zero. So clearly null space of T minus lambda is an invariant subspace. Now we want to show that null space of T minus lambda is also invariant under T star. We want to show that T star of null space of T minus lambda I is contained in null space of T minus lambda I. Now let us look at x is in, let us take x from null space of T minus lambda I. Then we have Tx equal to lambda x, or we can say that T minus lambda I at x is 0. Now since t is normal, t minus lambda is also normal, so we can say that t minus lambda I, norm of t minus lambda I x is exactly equal to norm of t minus lambda I star x, that is t star minus lambda bar I x. Now we know that t minus lambda x is 0, so this implies that t star x equal to lambda bar x. So we have taken x from null space of t minus lambda I, and we have shown that t star x is again in null space of t minus lambda I. That means null space of t minus lambda I is invariant under both t and t star, hence it is a reducing subspace. Now with these three results we can actually state the spectrum theorem for compact normal operators. We can follow the same steps as in the case of self-adjoint operators. Let T be a compact normal operator. Then there exists an orthonormal system of eigenvectors of T with corresponding eigenvalues lambda 1, lambda 2, lambda 3, so on. In fact, here also we can arrange them in the decreasing order in modulus, mod lambda 1 bigger than mod lambda 2 bigger than mod lambda 3, such that T has the following representation. This is similar to the earlier representation, but the only difference is that here lambda n's are complex numbers. If lambda n's are real, then we can conclude that T is self-adjoint. If lambda n is infinite, then we can say that lambda n converges to 0 as n tends to infinity. And here also the series of operators on the right hand side of this equation converges in the operator norm. Okay, the proof is same actually. Okay, now here also we can write the representation of T in terms of the orthogonal projections. So we can actually write T as summation lambda k pk, where k equal to 1 to infinity. Pk is nothing but projection onto null space of T minus lambda ki, and each non-zero eigenvalue has finite multiplicity, in the sense that dimension of null space of T minus lambda ki is finite. And spectrum of T in this case also is exactly set of all lambda n in n union 0 and we can also say that T is unitary equivalent to a multiplication operator as in the earlier case. So T can be written as U star M lambda U, where M lambda is a multiplication operator on L2 defined by M lambda of x1, x2, x3 is mapped to lambda 1 x1, lambda 2 x2, so on. Here lambda is exactly spectrum of T, converges to 0. So this is for every xn in L2. And here U is a map from H into L2 given by U of x is nothing but the sequence inner product x phi1, second component inner product x with phi2, and so on. In fact, U star of some y, here y is an element of L2, so we can say that U star of mu n is an element of L2, can be written as summation n equal to 1 to infinity mu n phi n for every mu n in L2. So this is another way of representing compact normal operator in terms of a multiplication operator, and this is a second representation of T, and this is the first representation. This is the third one. Okay, so this is about compact normal operators. Actually there is another way of proving spectral theorem for compact normal operators using the simultaneous diagonalization. Okay, suppose we have two bounded operators, A and B are bounded. If there exists an orthonormal system phi 1, phi 2, phi 3, so on, and complex numbers lambda 1, lambda 2, lambda 3, so on, and two set of complex numbers mu 1, mu 2, such that E and B are diagonalized with respect to the orthogonal system phi 1, phi 2, phi 3, so on. That is, Ax is summation n equal to 1 to infinity lambda n inner product x phi n with phi n, and B of x is nothing but summation n equal to 1 to infinity mu n inner product of x with phi n multiplied by phi n for every x in h. If A and B are represented by this orthonormal sequence phi 1, phi 2, phi 3, then we can say that A and B are simultaneously diagonalizable. In fact, we can easily check that A and B commutes with each other. A and B commute with each other. Okay. Now, using this also we can prove the spectral theorem for compact normal operators. So let us take, let T equal to A plus IB be the Cartesian decomposition of T A is nothing but t plus t star by 2 and B is nothing but t minus t star by 2i. If T is compact, then A and B are compact, and in fact they are self-adjoint also. Okay, and also T is normal implies AB equal to BA. So when AB equal to BA, all the invariants of spaces of all the eigenspaces of B are invariant under A. So we can say that now since A and B are compact and self-adjoint, we can write AX is summation lambda n inner product x with phi n multiplied by phi n. And of course B also can be represented in this way, but with respect to some other orthonormal system. We don't want that actually, we should get only one orthonormal system. So here what happens is null space of A minus lambda ki is invariant under B. Similarly, if we take eigenvalues of B, then the corresponding eigenspaces of B are invariant under A. Now using this, actually we can get a common orthonormal system for both A and B, and we can get the result that we have proved just now. That is, this result we can get. Okay. So this is about simultaneous diagonalization for compact normal operators. Okay. So I'll stop here. Thank you very much.